Okay, so before going into the new stuff today, we're continuing section 10.3. I wanted to go over some of the homework problems. So there's two homework problems I wanted to go over. It's being like kind of like this weird triangle problem where it wants you to find the area of the sum of all these triangles, or I should say the sum of all the areas of the triangles. And then there's another one where it wants you to compute some partial sums, which is going to depend on the power of n that you have. From what I've seen, like this homework seems to have been going well. I think people have been able to finish it like pretty quickly in comparison to like the differential equation problems. There's kind of like less ambiguity about how to write the answers as well. So the homework's been going pretty well and the problems are pretty fast, but I just wanted to go over these problems. I think this is kind of the hardest one right here. So for this problem, it wants you to compute the total area of the triangles in the figure below, where we have that h is going to be equal to 37. Like h is just going to be the height of all the triangles that you have. And so this is really good. The only thing that's going to change from problem to problem. So your problem might be like 42 or 43. But at the end of the day, all you have to do is just change like one of the numbers at the end. Right? So we're letting h be equal to 37. And so you should be thinking, like before even going through and writing out what this is going to be as a series, it's a good idea to just record what the areas of these triangles are going to be, and then try and come up with a formula that would describe like the general like nth triangle or the area of the nth triangle. So you can just write out what the area of the triangles are going to be. So the first triangle we're going to look at is going to be this triangle here. And just to clarify, like in the figure in the homework, like the dots here are really small. So like we're not looking at triangles that go to the right. We're only looking at the triangles that are like diminishing in area, not ones that are going like getting larger over time. That was like a source of confusion last semester when I was teaching this. Okay, so I'm just going through like the areas. So the area of the first triangle, I mean, doing this is all like it's pretty straightforward. It's just a matter of combining them as a sum at the end. So the area of a triangle is half of the base times the height. So we always have 1/2 times the height. So the height of all these triangles is equal to 37. So this is going to be constant for each of the triangles. It's always just going to end up being 37. So this will be 1/2 times 37. And then the base of this triangle is given by 1/2. So this is times 1/2. I'm just going to leave it like this. You could multiply and say this is 37 over 4, but I just want to record like what's changing over time. We're going from one triangle to the next. So the second triangle is going to be the following. So we still have half of base times height. We still have this 1/2. We still have this 37. The only thing that changes is going to be the base of the triangle. We're going from 1 over 4 to 1/2. So the total distance is given by 1 over 4. You can do 1/2 minus 1 over 4 to determine that this will be 1 over 4. And then I'll do one more before writing out the general equation. So the third triangle is going to look like this. So this is going to be 1/2 times 37. Again, half of base times height. These two terms always remain the same. And so the term that's changing is going to be, again, the base. So we're looking at this triangle. The base goes from 1 over 8 to 1 over 4. So this is going to be 1 over 8. And so what you should be noticing is the bases of the triangles are always diminishing by half. So you're going from 1/2 to 1 over 4 to 1 over 8. You can also write these terms. I mean, we need to start thinking in terms of like, what is our series going to look like? And so you should note that this is 1 over 1/2 or 1 over 2 to the first power. This is 1 over 2 squared. Or maybe let's write it like this. So this is like 1/2 squared. And then this is 1/2 cubed. I'm not saying like we're multiplying these terms. It kind of looks like I'm saying I'm multiplying them. I'm just saying like 1 over 4 is the same thing as 1/2 squared. I just ran out of space to write this. And so now let's just think about what the nth triangle is going to look like. And so you should be noting like the first triangle, the base was 1/2. The second triangle, the base was 1/2 squared. The third triangle, the base was 1/2 cubed. So like the 3 here corresponds to the 3 here. The 2 here corresponds to the 2 here. So you should note or be thinking like the area of the nth triangle is just going to be 1/2 times 37 times 1/2 to the nth power. And then like this is the hard part. Like once you determine the equation, it's now just a matter of actually computing what the series is going to be. So the total area is it the sum of the area of all of these triangles, and we have infinitely many triangles. This is going to be equal to the series. So the only thing that's changing is the power of our base. We're going from 1 to 2 to 3. And so we're starting at n is equal to 1 based off of the fact that this is 1/2 to the first power. So this is going to be n is equal to 1 going to infinity. And then this is going to be 1/2 times 37 times 1/2 to the nth power. And so neither of the first 2 terms of the product rely on n. So you can bring these terms outside of the sum. This is an important thing to recognize that you can do. Like you want to reduce as much clutter as possible inside of the series. So this is going to be 37 over 2 times the sum from n is equal to 1 to infinity of 1/2 to the nth power. And now we just have a geometric series, right? This is a geometric series where the ratio is just equal to 1/2. And so because the ratio is equal to 1/2, it's less than 1. So we know this is going to converge. And we know that this is going to converge to the first term over 1 minus the ratio. So this is going to be equal to 37 over 2 times the first term of the sequence. The first term is whatever you get when you plug in whatever this first index is into your sequence. So this is going to be just 1/2. And then this is going to be 1 minus the ratio, which also happens to be 1/2. So this is really 1/2 over 1/2. That's equal to 1. So this ends up just being equal to 37 over 2. And so that's going to be what changes. Like our height was 37. Your height might be like 42 or 43 or something, but I mean, you just change the numerator, right? So this is, I like this problem. Like I think I have it on the group board tomorrow. I have it on the final exam review. There'll probably be there'll be a problem similar to this on the final. So it's like important to know how you do this kind of stuff, right? Except instead of on the final, it might be like circles instead of triangles. Any sort of like geometric shape where you know how to compute the area, right? And you're just like recursively just like shrinking things. Okay, any questions about this problem? Okay, yeah, I think this is kind of the hard problem of the homework. The other ones are more like this other problem I want to go through. So it's like if you know how, or you kind of understand what's going on when, like with these problems, they're really fast. Like this kind of problem, like it takes like a minute or two if you understand like what it's asking. And so for this one, it wants you to find the nth partial sum of the following infinite series. And so it's really asking you to find like a general formula of like the first, if you take the sum of the first n terms of your sum. I should use, instead of lowercase n, let's use uppercase, right? It shouldn't match, like I already used n as like the index here. Okay, so the first term, S1, is this going to be what you get when you plug in n is equal to 1 here? If you plug in n is equal to 1, you get -1 to the 1 minus 1. So this is -1 to the 0th power. So this is equal to 1. And then S2 is just going to be what you get when you plug in like S1, which is 1, plus what you get when you plug in the term after n is equal to 1. So what you get when you plug in n is equal to 2. So the next term is going to be -1 to the second power minus 1. This is equal to 1 minus 1, which is going to be equal to 0. And so this is the trend that's going to occur, right? Like for s is equal to 1, this was equal to 1. So like for the odd term, it was equal to 1. For the even term, it was equal to 0. Let's see if this ends up holding for, I guess, like the next odd and even numbers. So S3, this is going to be equal to 1 minus 1, right? This is like n is equal to 1, n is equal to 2, and then plus what we get when we have n is equal to 3. So when n is equal to 3, we have minus 1 to the 3 minus 1. So these terms cancel out with one another. And then we have minus 1 squared, which is equal to 1. So this is going to be equal to 1. And then S4, this is going to be 1 minus 1 plus 1, and then plus minus 1 to the 4 minus 1. So these terms cancel out. This is going to be equal to 1 minus 1, which is equal to 0. Right? So this is the trend that's happening, right? For the even or for the odd terms, the partial sum is equal to 1. For the even terms, the sums are equal to 0, right? Like they end up just like canceling out. And so we end up getting the following as our answer. So the nth term, like the nth partial sum, it's really going to be like 2. Like there's 2 cases to this. It's either going to be equal to 0, or it's going to be equal to 1. So it's equal to 0 when we have that n is even. Then it's equal to 1 when we have n is odd. Right, just kind of generalizing the pattern that's occurring here. Okay, I think on the actual homework, it's multiple choice, so you can just brute force this if you really wanted to, but it's like an important skill to be able to determine like what the nth partial sum is going to be, right? Like you need to be able to read off what this is going to give you in terms of like the partial sums. Okay, any questions about this problem? Okay, I think like the other problems on the homework, they're mostly just going to be geometric series or using like the divergence test that we talked about on Friday. Okay, so there's just 2 homework problems. Next, we'll go back into, we already started section 10.3 a little bit. We talked about one of the major tests from this section, that being the integral test. And so I guess really this week, we're just looking at a bunch of different tests for determining series convergence. And I think there's going to be like 6 or 7 different tests that you're going to have to be familiar with. It's going to seem like a lot, but at the end of the day, it's better than using like the partial sequence or like the partial sum way of determining convergence. Does anyone need the notes before I continue? These are the notes I handed out on Friday. If you're here on Friday, you should have the notes. Okay, so just as a quick reminder of what was going on. So the first test we looked at was the integral test. This one shows up every now and then. Like there'll probably be on at least one problem on the exam where you have to use the integral test. Usually you want to use the integral test when you have any sort of series where the sequence is a function that's easy to integrate. Like the integral test would come in handy here. In particular, like usually you want to do it when you have like 1 over n or like 1 over n squared or something like that. Like this is kind of like, if none of the other really nice tests that we'll learn later on doesn't apply, you want to use the integral test. That's kind of how I think about things. And so what the integral test is telling you is that if the integral of f of x converges, where f of x is the function that gives you your sequence, then the infinite series is going to, and then similarly, if this diverges, if the integral diverges, then it implies that the sum is going to diverge as well. So we went through a couple of examples. The most important application of the integral test is going to be showing that this series ends up diverging. This is something you're going to want to keep in mind. This is like you want to always remember a geometric series, but you also want to remember like series of the form of 1 over n to some power. Those are like the most important series to remember, whether or not they converge or diverge. And so using the integral test, we showed that the sum of 1 over n ends up diverging, right? So you just rewrite 1 over n as 1 over x, and then you just take this integral. It's an improper integral, so you like do this limit of the integral, and it ends up being infinity. So as the integral diverges, we were able to conclude that the following sum is going to diverge as well. And then similarly, for the next problem, we were able to show that this series ends up converging due to the fact that this integral ends up converging, right? And so we showed that the integral of this function ends up being equal to 1 over 4. That doesn't mean that the actual series converges to 1 over 4. It just means that the series converges. We don't know what this converges to yet. We'll see later on. Okay, so this is where we left off on Friday. We went through these 2 examples. And so this theorem it's one of the most important theorems from this section. And it should be like somewhat intuitive. I mean, there are parts of that are hard to understand, I guess, but really like this is just going to be convergence of P series. And so this is going to tell you that the infinite series, if you ever have an infinite series of the form of 1 over n to the pth power, then this is going to always converge if we have that p is greater than 1, and it's going to diverge otherwise, right? So if you have like 1 over n squared, 1 over n cubed, 1 over n to the 4th power, you can immediately conclude that it's going to end up converging. But if you have like 1 over n or 1 over n to the 1/2 power, you can immediately conclude that it's going to diverge. So you can always just refer to this theorem, right? You don't have to actually go through, like you don't have to do the integral test to prove that this diverges anymore. You can just be like, by this theorem, we know that this is going to converge pretty much, or depending on what your p is. And it should be like this is actually familiar. Like this theorem 3 is just rewriting what we already did in section 7.7. Let's see if I can, yeah. So like in section 7.7, like we had the following theorem, which tells you when integrals of this form are going to converge. Like the theorem we have here that we talked about in theorem section 7.7 is equivalent to what we have here, right? By the integral test. So this is important to keep in mind. So just looking through like 2 examples, I mean, I already said this verbally, but like when p is equal to 1 over 3, i.e. the power of n is 1 over 3, we're really saying like this is the series of the cubic root, or the cube root of like 1 over n. And so because p is less than 1, we can immediately conclude that this is going to diverge. And if we had p is equal to 2, i.e. we looked at the series of 1 over n squared, p is greater than 1, therefore we already know this is going to converge. Right, so this is really important, like it'll show up all the time. Particularly it'll show up when we're doing the comparison test. And this is like this comparison test, I mean, I don't want to think too much in terms of like integration, but should be thinking in terms of like the comparison test that we're talking in terms of series. Like it's really like this comparison test that we had for improper integrals as well, right? At least it's the same idea conceptually. So this is going to be a really useful method for determining convergence of a positive series, i.e. like all the terms in your sequence are greater than 0. And so this is a pretty intuitive test, or at least I think it should be pretty intuitive. So we're going to assume that there exists some sort of m greater than 0, such that for all indices past this number m, we always have that a sub n is less than or equal to b sub n. Really, I mean, I'm kind of like making things technical by saying we have like this condition on the indices. You should just be thinking, like if we have one sequence, b sub n, where the terms are greater than the terms a sub n, then we end up having the following. So if we have that b sub n, or this series, b sub n, if this converges, then it must imply that this series consisting of the sequence a sub n is going to converge as well. This should be intuitive because we're saying that b sub n is larger than a sub n. So if you take the sum of the numbers that are larger and it ends up converging, then the terms that are smaller should also converge as well, right? That's what I'm saying. Like it should be intuitive. Like these are bigger numbers than what we have here. So if this is less than infinity, this has to be less than infinity. And it's also worth noting that we're only assuming positive series here. If we were assuming that we didn't have a positive series, then technically a sub n could go to minus infinity. But again, we're only considering a sub n greater than or equal to 0. And then similarly, if we have that a sub n, or if this series of a sub n diverges, then this implies that b sub n has to diverge as well. The way of thinking about this is if the smaller sum, or the sum of the smaller terms ends up going to infinity, then the sum of the larger terms has to go to infinity as well. So kind of the way of thinking about things. Okay, so the idea is pretty intuitive. Despite that, I think like these problems are kind of the less intuitive ways of determining convergence, actually. So for this one, it's asking us whether or not the following series is going to end up converging. And so how to think about this is, I mean, we have like, I'm saying like this is a problem in the comparison test like subsection. So I guess we want to use a comparison test, but there's like other ways of thinking about like whether or not we should be using the comparison test kind of embedded within this sequence. I guess there's like two sequences that we're familiar with. There's one over the square root of n, which we know is going to diverge because it's like it's a p series where n is equal to 1/2. But then we also have 1 over 3 to the n. This is going to be a geometric series where we have that n, or we have the ratio is 1 over 3. And so like what you want to do is you want to take this series or like the sequence, like ignore the sum at all at this point. Like just think in terms of the sequence that we have. And we just want to compare it to another sequence that we already know about. And so let's just start off by thinking about 1 over the square root of n times 3n, or 3 to the nth power. So this is our a sub n. Like this is the original sequence that we have. And now we want to compare it to another sequence b sub n. And so you want to pull from this sequence another sequence that you know how to deal with. So we're going to say this is less than or equal to another sequence. And I guess like I said in the beginning, there's two options. Like there's 1 over the square root of n, and there's 1 over 3 to the nth power. You need to think in terms of which one will be more useful for you. Like if we said that this was less than or equal to 1 over the square root of n, it wouldn't really give us any useful information, right? Like if we said this, I'm going to erase this later on. Like this is kind of like the wrong choice. Because like if you think about it, we already know that this series, this goes to infinity. And so all we're saying, like if we chose this as our sequence, all we're saying is that the sum here is less than or equal to sum here, but this is equal to infinity. So all we're saying is that this sum is less than or equal to infinity. That doesn't really tell you anything, right? It means it could be finite or it could be equal to infinity. So like you don't want to use this one here. And so you want to go with the other choice that we have. We want to go with 1 over 3 to the n. And I guess before, like I'll write this out and then I'll explain it. So let's consider this comparison instead. And the reason why we know, I mean, I should go into the reasoning behind like why we know this is less than or equal to this. Like if you think about the denominator here, all of our values of n are greater than or equal to 1 because we're starting at the the sequence starts at n is equal to 1. And so what we're really just doing by multiplying by the square root of n is making it so we have a larger denominator from what we have over here, which is why this sequence is always less than or equal to this sequence right here. Like when n is equal to 1, they're going to be the same. But when n is equal to like 4 or something, you have 1 over 2 times 3 to the 4th power instead of just having 1 over 3 to the 4th power. Okay, and so this is going to be the comparison that we have. So this is going to be our a sub n. This is our b sub n. And now to determine the convergence of this series, we just need to determine that this series converges. And I mean, we already know this converges. This is just a geometric series where r is equal to 1 over 3. So, I mean, you could just say, you can stop there and just be like, this converges as a geometric series with r is equal to 1 over 3. Right? And this is the same thing as, instead of doing like 1 over 3 to the n like that, you can do it like this. And so this would immediately imply, so we're saying that this finite sum ends up being, or this infinite sum over this sequence ends up being a convergent series. So this has to, or ends up being a finite number. So the sum over here has to be finite. So I'll write this out in more detail, but I'm just saying like on the exam, you can write it this way and you won't get in trouble at all. And so this implies that the series from n is equal to 1 to infinity of 1 over the square root of n times 3 to the nth power converges as well. Okay, so that's kind of like the fast way of doing it. You can just leave it like that on the exam and you would get full credit. But like another way of writing, just like writing things out in more detail. right? So we have this inequality. So what I was saying before is like this sum of 1 over 3 to the nth power, where n is equal to 1, and then this is going to be infinity. We know that this as a geometric series is going to be equal to the first term, which is going to be 1 over 3 to the first power over 1 minus 1 over 3. So this is equal to 1 over 3 over 2 over 3, which is just going to be equal to 1/2. So we know that this series converges to 1/2. And so what this implies is that we have that this sum of 1 over the square root of n times 3 to the n is equal to 1 to infinity. What we're saying is that this is less than or equal to this sum for like n is equal to 1 to infinity of 1 over 3 to the nth power, which we just proved to be equal to 1/2. Wait, this is, oh, there should be 2, right? As I was going to say, this doesn't make any sense because like when n is equal to 1, oh wait, I don't know how to do math anymore. Okay, I think it is 1/2. Okay, I was thinking about things. Okay. Yeah, because like the 3's cancel out and you get 1 over 2. Never mind. I was thinking my index was like 0. I was like, wait, this is like 1, and then how can like 1, like whatever. Ignore the last minute. Okay, and so this is equal to 1/2. So what we're saying is like this series ends up being less than or equal to 1/2. And so this implies that 1 over the square root of n times 3 to the nth power, where n is equal to 1 to infinity, converges. Even then, like the ultimate value here doesn't really matter. As long as it's finite, we can conclude this converges. And I guess we get an upper bound out of it as well. So we know this series ends up being less than or equal to 1/2. This is kind of like the long-winded way of doing things. And usually I'm not going to do that. Like if I just have like a geometric series, I'm just going to write it out in the following way. But I thought it would be worth going through at least once. Okay, any questions about this example? Okay, so that's why it's important to remember like what's going on with the geometric series. Like on the final, I'll ask you like point blank, like show what like a geometric series converges to. But then you might also have to use like geometric series for the comparison test problem as well. Okay, this next one's a little bit trickier. So for this one, it wants you to determine whether or not this series is from n is equal to 2 to infinity of 1 over n squared plus 3 to the 1/3 power ends up converging. Later on, we'll come up with better ways of determining whether or not this series converges. This is kind of like the hard way of doing things. We'll come up with easier ways later on to do this. I think in section 10.4 or 10.5. And so we're going to use the comparison test for this one again. So the idea is going to be like, let's just think in terms of like what's going on with the denominator. Right, so like this is the original sequence that we have. And it's a little hand wavy, or maybe I'm going to be like a little like loosey-goosey with this. But like we want to find a sequence that this is going to be less than or equal to. Or, hold on. Oh, actually, this is like the original sequence we have. This is our a sub n. And so we need to be thinking in terms of even like my labeling. Okay, never mind. I'm thinking too much. Okay, so this is like the original series that we have. Like, let's just think in terms of like what's going on with the denominator, right? We kind of have like an n squared plus 3 to the 1/3 power. Like the plus 3, it doesn't really contribute all that much. And so you should be thinking there's kind of like this n squared to the 1/3 power. And so this is kind of like having 1 over n to the 2/3 power. All right, this is like kind of what we have at the moment. And we know that this ends up diverging as a p series where p is equal to 2 over 3. Like this is less than 1. So we know that this is going to end up diverging. So you should be thinking like this should end up being a divergent series. And so if we want to show that this is going to be a divergent series, we should actually be doing the inequality like this. Like we want to show that it's going to be greater than or equal to something that's going to end up diverging. And so you should be thinking in terms of a nice series that we already know ends up diverging that kind of looks like this. And so one possibility, and there's a number of possibilities, but one is going to be just doing like 1 over n, like this. Right? Because I mean, this is essentially just like 1 over n to the 2/3 power. And then like 1 over n, like the n is going to be a larger number than like n to the 2/3 power. And so let's just say this is like a claim. I mean, if you're writing this on the exam, I would be fine with you saying like this inequality is fine, like this ends up holding true. But let's actually prove that this ends up being the case here. So again, on the exam, I'm fine with you leaving your answer. Actually, I don't know. I don't want to go through the whole detail. You can do this. You can leave your answer like this. I was going to go through and like do like derivatives and stuff like that, but in the interest of time, I don't feel like that's very necessary. Right. So the big idea is we have that this series is approximately equal to this series due to like n squared to the 1/3 power. And we know that 1 over n, the denominator is larger. So it's going to be less than or equal to what we have here. And so the main point is the following. So we have that this series from n, we're starting at n is equal to 2 to infinity of 1 over n. We know this is going to be less than or equal to the series from n is equal to 2 to infinity of 1 over n squared plus 3 to the 1/3 power. And so the point is, like, this is a p series where we have that p is equal to 1. So we know that this diverges already. And so what we're really saying is we have that infinity is less than or equal to the sum from n is equal to 2 to infinity of 1 over n squared plus 3 to the 1/3 power. And so this must imply, I mean, if this is greater than or equal to infinity, this has to be infinity, right? And so this means that our series is going to diverge. Yeah, so in the notes, I go through this in a little bit more detail, explaining why this ends up being less than or equal to this. You can write things out in terms of like derivatives, and you can take derivatives and show, like, if you do the difference, it's less than 0. So there's like a decreasing function. But I think the idea is intuitive enough, right? That 1 over n is less than or equal to this term. And these two things are approximately equal. So you can, like, you end up having the following inequality. And then the comparison test does the rest. Okay, any questions about this example? Okay, yeah, so it's kind of like hand wavy a little bit, but on the next page, we'll come up with a way, like a better way of kind of evaluating these comparison tests or doing these comparisons. Okay, so before going on to the next page, next we want to determine the convergence of the following series. And so I'll say, like, in chapter 10, the hard part isn't always just going to be like taking a series and applying a test to determine whether or not it converges. Like, usually the hard part is going to be determining what test to use in the first place. And that's kind of this is like the first problem we have to think in terms of like what test is going to work best for us. And so we have this series like n is equal to 2 to infinity, and then we have 1 over n, and then times natural log of n squared in the denominator. And so if you look at this, I mean, usually the first thing you would want to do is you would want to do the divergence test. So you would want to take the limit as n goes to infinity and see if this goes to 0 or not. You can quickly see that as n goes to infinity for this sequence, this is going to be approaching 0. So it's inconclusive. Like, we don't know if it's going to diverge or converge based off of the divergence test. And now we can use one of the other tests that we know. Like, we see this isn't a geometric series. We also see that it's not quite a p series because we have this natural log squared. And so we're kind of left between the integral test and the comparison test. And so you might be thinking like we'll use the comparison test because we have the following inequality. So we have 1 over n times the natural log of n squared. This is less than or equal to 1 over n because we have like this additional positive term in the denominator. But again, you should be thinking like we do have this inequality. This is true. But if you take the sum of both sides, this is just going to be equal to infinity. So the only conclusion you can reach is that this infinite sum is less than or equal to infinity, which is something you should already know, right? Like, I mean, it's either going to be a finite number or it's going to be infinity. And if it's less than or equal to infinity, it means it's a finite number or it's infinity. So it's like, it doesn't tell you anything. So we don't want to use the comparison test here. So comparison doesn't work. And so, I mean, there's only one test remaining. That's the integral test. And I feel like the integral test is kind of like nothing else has worked. So I'm just going to integrate it and see what happens pretty much. Or, I mean, you can also just look at this and be like, the integral of this isn't going to be that bad. So we're going to define f of x. So we're going to do the integral test. Let me write that out first. So we're going to do the integral test. And so we're going to define f of x to be equal to 1 over x times the natural log of x squared. And now we're just going to integrate this function from n is equal to 2 to infinity. Remember, like the bounds of integration will always match up with your indices for the sum that you're looking at. And so we're going to look at the infinite sum from 2 to infinity of 1 over x times the natural log of x squared dx. And so to compute this integral, I can just let u be equal to the natural log of x and everything works out. So this is going to be u is equal to the natural log of x. Du is then just going to be 1 over x dx. We have a 1 over x dx here. So we're left with 1 over u squared. So we get the following integral, and you need to change the bounds of integration. I mean, I should be writing this out as a limit, but I'm too lazy to do that. So this is going to be natural log of infinity, that's infinity. Natural log of 2, it's the natural log of 2, so this becomes the natural log of 2. And then this is going to be u to the minus 2 du. And then you integrate this, so this is going to be equal to minus u to the minus 1 from the natural log of 2 to infinity. This is kind of like, I mean, I do this all the time now, and I tell you not to do it, but I'm just going to say this is like 1 over infinity minus 1 over the natural log of 2. That's what you get when you plug in these numbers. And infinity is not a number, but I don't know. You'll get like the right idea. You write things out in this way. And so this term, is this equal to 0? This is like minus 1 over the natural log of 2. So this is 1 over the natural log of 2. The main point is that this is less than infinity, right? This is a finite number. And so this immediately implies that the corresponding series is going to end up converging as well, right? And so this is going to imply that the sum from 1 over n to the natural log of n, or natural log of n squared, starting at n is equal to 2 to infinity, this converges as well. Right. So I think that's kind of like the integration test or integral test. It's kind of like a test of last resort, pretty much. It's not, it usually isn't like the first thing you want to try out, but sometimes it works out pretty well. Like the integral itself wasn't so bad here. Okay, any questions about this example? Okay, so the final test from this section before going into section 10.4 is the limit comparison test. You should be thinking this is kind of how you want to do the comparison test. Like I introduced the comparison test. We went through a couple of examples. Now just like, well, I was going to kind of say it jokingly, but like now completely throw that away and just always think in terms of the limit comparison test now. The limit comparison test kind of gives you a formal way of doing what we were just doing before, like when we were writing out these inequalities, right? And so this is what the limit comparison test is going to tell us. So the next test for convergence is going to involve a comparison between two series, the series of a sub n and b sub n, via a limit of ratios, a sub n over b sub n of the terms in the following series. So this is what the limit comparison test is telling us. So we have L. We're always going to define L to be the ratio of the two sequences that we have. So this is going to be the limit from n goes to infinity of a sub n over b sub n. And so there's three different scenarios that can end up happening. And I'll just tell you, it'll determine whether or not your sequence or series is going to converge. So if we have that L is greater than 0, then we're going to have that the series of a sub n converges if and only if the series of b sub n converges. This is going to be the most common case. This is really the one you have to remember. The other cases don't really show up all that much. The second case tells you that if L is equal to infinity, and we have that this sum of a sub n converges, then b sub n ends up converging. And then the last situation tells you that if L is equal to 0 and b sub n converges, then a sub n or this series ends up converging. So you need to be thinking in terms of like how this makes sense is you should be thinking in terms of like, in terms of limits, obviously. So what we're saying, for instance, if we have this, or maybe let's look at this one first. If we have like L is greater than 0 and we have that a sub n ends up converging, right? We're saying that this limit ends up being some sort of finite number. So that tells you that this sequence right here, it tells you this cannot be going to infinity. Otherwise, this would be equal to 0. And it can't be going to 0. Otherwise, this entire thing would be going to infinity. That's the idea here. And then this part is really just the converse, like b sub n is blowing up really quickly. It's blowing up faster than a sub n. So if this converges, this implies that the series of a sub n has to converge as well. And then if L ends up going to infinity and a sub n converges, then it's pretty much implying that b sub n is going to be like b sub n converges to 0 over time. It's kind of the way of thinking about it. But really, it's like the first bullet point is the one that you want to remember. And so how this works out in practice is going to be the following. Joshua, can you close the door? I'm getting, like, there's a lot of whispering. Thanks. Okay, and so for this, it wants you to show that the following series converges. And so the game that we were playing before with the comparison test is exactly what we're going to be doing here as well. Right, so we're doing the series of n is equal to 2 to n to the 4th power minus n minus 1. And so we're just going to define initially a sub n. Like a sub n is always whatever your original sequence is going to be. So this is n squared over n to the 4th power minus n minus 1. And so how you determine, like we're always going to have two sequences. We have a sub n, and then we should also have b sub n. How you determine what your b sub n is going to be is, you play the same game that we just were playing, right? Like n squared over n to the 4th power minus n minus 1. Like really the big players here, like we don't care about like n and 1. Like the big players are n squared, then n to the 4th power. So this is approximately equal to n squared over n to the 4th power, which is just equal to 1 over n squared. And so this is what your b sub n is going to be. Right? Like b sub n is kind of like your ideal version of a sub n. Like it's your a sub n without the trash, pretty much, without like the minus n and the minus 1. Right? It's only like the stuff that actually matters. Like i.e. like the leading term of like the leading powers you have for n in the numerator and the denominator. And so now what we're going to do is we're going to take the limit as n goes to infinity of a sub n over b sub n, and we want to see if the limit ends up being greater than 0, equal to infinity, or if it ends up being equal to 0. And so now we take the limit as n goes to infinity of a sub n over b sub n. This is the limit as n goes to infinity of n squared over n to the 4th power minus n minus 1 all over 1 over n squared. And so if you compute this limit, well, before doing the limit, let's simplify things a little bit. This is the same thing as doing n squared times n squared over n to the fourth power minus n minus 1 times 1. So this ends up being equal to n to the fourth power over n to the fourth power minus n minus 1. And now if you want to compute this limit, I mean, all you have to do is just compare, like we have an n to the fourth power in the numerator. That's the largest power of n that we have. Then we have an n to the fourth power in the denominator. And then everything else doesn't really contribute all that much. So this limit, it's really just the same thing as doing the limit. This is like Calc 1 stuff. Of n, I think it was like section 2.7 or 2.8. It's like n to the fourth power over n to the fourth power, which is just equal to 1. So we ended up finding, oh, maybe I should write out, I didn't say that. So this is our L, right? Like L is just equal to this limit right here. So we just found that L is equal to 1. So that tells us that L is greater than 0. And so what this tells us is that our series over A sub n is going to converge if and only if the series over B sub n ends up converging. B sub n is equal to 1 over n squared. We know this is a P series where P is equal to 2, so we know it converges. So just writing this out, so we know that n squared, or the series of n squared over n to the fourth power minus n minus 1 converges if and only if 1 over n squared converges. And then we know that this converges because it's a P series where P is equal to 2. Right. Again, like we're just using the, I'll scroll back down after I'm done saying this, but we're just using this theorem. Like this theorem is really important. As you see, like it shows up all the time already. Like we already talked about it today, but we've used it at least like 3 times in today's class. And that's a trend that's going to last forever pretty much. Okay, so we know that this series converges. So that means this series has to converge as well, is the main idea. Okay, any questions about this example? Okay, so that's where we'll stop. We'll do one more example with like this limit comparison test tomorrow. But it plays out in pretty much the exact same way. And then one other thing, I have office hours today, but I don't have office hours from 11 to 12 like I usually do. It'll be from 12 to 1:30. I have to proctor an exam, so